Welcome back, students. In this video, we're going to explore the relationship between energy and frequency of electromagnetic radiation. So far, we've talked about how wavelength and frequency are inversely related. That is, wavelength increases, the frequency decreases, and vice versa. And in the previous video, I mentioned how energy and frequency are directly related. So as frequency increases, the energy of electromagnetic radiation also increases. Now, before we get into the math of how to calculate energy from frequency and so forth, I have a very short paragraph, and I will say right now that this is probably one of the shortest explanations of the beginning of quantum theory that I could possibly write. And in distilling it down to just a few sentences, I have left out so much context and detail and a lot of the very interesting development of quantum theory here. So there's a lot of additional reading in your OpenStax e-text on Planck, on blackbody radiation, on Einstein and the photoelectric effect. And I'm also going to link to 2 additional videos at the end of this video for those of you who would like a little bit more information about this, because it is pretty amazing how these researchers in the early 1900s reasoned their way from the classical model of physics to introduce this new quantized approach to energy that we now call quantum theory, and how a number of their innovations, by using this quantum theory, were able to resolve problems with the classical theory that had not been able to be resolved before. So let's just fill in these gaps, and again, you can do some additional reading and watch additional videos, but I just want to set the stage for the math that's going to follow, okay? So when investigating objects that had been heated, so we're heating an object. For example, you might be heating a piece of iron in a forge until they glowed, and we know that if you heat something, then you can get it to start glowing. These objects were called black body. B-L-A-C-K-B-O-D-Y. Black body objects, and the glowing that they were given off is called radiation. Again, not radioactivity, but the radiation that we've been talking about of electromagnetic radiation. So this is talking about black body radiation, when you heat up an object until it glows. So Max Planck was a researcher around the turn of the century, around 1900, and he was studying black body radiation, and at the time the classical model of physics was not able to adequately model or explain the results in blackbody radiation experiments. Well, Max Planck introduced a new mathematical formula to model the frequency and wavelength and energy of blackbody radiation by introducing what's called quantum theory. So Planck found that energy given off in blackbody radiation was best modeled if you considered it as only being occurring in multiples of a certain amount of energy. And that is, in blackbody radiation, you were not given infinite frequencies or wavelengths of radiation that was being given off. You were only given certain discrete wavelengths and frequencies that were given off. And so he modeled this blackbody radiation mathematically by assuming that there was a smallest amount of energy that could be called a bundle or a packet of energy, and that energy occurred in discrete amounts, and that discrete amount is called a quantum of energy, and therefore energy is said to be quantized. So what does quantum and quantized mean? Quantum just means an amount, and quantized means that something occurs in a discrete amount and not all possible amounts. To make more sense of this, let's think about money. Our money is quantized. Here in the United States, the smallest amount of money that I could give you is 1 penny. I can't give you a half of a penny or 3/4 of a penny or 0.02 pennies. I can give you 1 penny or 2 pennies or 3 pennies. So our money is quantized because it has a smallest amount, and all monetary amounts are simply some multiple of that smallest amount. So this is the breakthrough that Max Planck made in the year 1900, and it was a way to explain a problem with the classical model of physics by using this quantized approach, or quantum theory. 5 years later, Albert Einstein expanded on this quantum theory by using Max Planck's math to explain the photoelectric effect. And I will link a video also on the photoelectric effect. And so Einstein's explanation using quantum theory explained the photoelectric effect in a way that classical mechanics was not able to do. Einstein's method of explaining this using quantum theory showed that light is also made up of these little bundles of energy because his quantized mathematical approach provided a better explanation for the results, the experimental results that were seen in the photoelectric effect. So the small quantum, or the smallest quantum or amount of light, is called a photon. So here again, I have very briefly covered 2 of the early developments in quantum theory by Max Planck and by Albert Einstein, which showed the benefit and the utility of the quantum theory to explain experimental results that before that time classical mechanics and classical physics had not been able to explain. So this is the early days of the quantum theory. For now, let's deal with the basic equation that Planck came up with. He said that energy, E, and that's going to be in joules, equals some constant H, which we will call Planck's constant, and it has a value and a unit, it's joule seconds, times nu, the frequency. So that H is Planck's constant, the energy in joules, and this is nu, the Greek letter nu, and it means frequency. So let's notice the units of measurement here. Energy is in joules. Planck's constant is in joule seconds, not joules per second, but notice that joule seconds means that joules and seconds are both in the numerator. Joule seconds. And then times frequency, which is inverse seconds, or 1/seconds. So you can see how these seconds will cancel out, leaving us joules for the energy. Okay, with this in mind, I have a sample problem, and the sample problem is asking you to calculate the energy of a photon of light with a frequency of 6.5 times 10 to the 14th inverse seconds. So I'd like for you to do that in this little space right here. As always, we write the equation that we're going to use first, and then plug in numbers, and then give the answer with the correct sig figs. Pause the video, do that work, and when you're done, resume the video, and I'll finish that. So coming back to this, E equals h nu, there's the energy, equals Planck's constant times the frequency. And so I'm going to start plugging in values to calculate this energy. Planck's constant, 6.626 times 10 to the, and that is a negative 34. Make sure we see that. So Planck's constant, 6.626 times 10 to the negative 34 joule seconds. The units are just joule seconds. That doesn't mean we have to multiply joules times seconds. It just means that that's the unit. They're both in the numerator. Joule seconds. Times the frequency. Frequency is given here, 6.5 times 10 to the 14th inverse seconds. And you'll see that the seconds here and the inverse seconds there will cancel and leave us with joules. And doing this math and then rounding to, let's see, 4 sig figs, 2 sig figs, we want to round to 2 sig figs, gives us 4.3 times 10 to the negative 19. And that's going to be in joules, right? Because the seconds and inverse seconds cancel, leaving joules. And that's good because energy should be reported in joules. Correct sig figs, correct units. And there we go. Small amount of energy, right? Times 10 to the minus 19. Does that make sense? Yes, because this is just the energy of a single photon of light. So we would expect it to be a small amount of energy. So I'd like to point out a couple of things here on the back of your periodic table. You're going to find some useful information. We have provided some of these equations for you. There's the C equals lambda nu. As you recall, that's the relationship between the wavelength and the frequency through the speed of light. We've given you the speed of light here. And here is Planck's constant right there, 6.626 times 10 to the minus 34 joule seconds. And you'll see the Planck equation right here as well. The energy in joules equals Planck's constant times the frequency in inverse seconds. Okay? So you can see that we've provided some of that information for you. Now, this takes us to being able to bring it all together. So now we've had equations where we've had E equals h nu that will relate energy and frequency. We've seen the other equation, C equals lambda nu, which relates wavelength and frequency. So as you might imagine, we could have an equation that combines both of those equations into a single equation that would relate energy and frequency and wavelength. And yes, there is an equation that would do that. However, we're not going to include that equation. What I would like to do instead is I would like to be able to use the two equations that we've learned so far and to be able to use them in sequence when and as we need them. And I hope by doing it that way that it will make a little bit more sense, that it will track a little bit more intuitively about where these relationships come from, rather than just lumping them all into one equation where the relationships might not be so intuitive. So, just as a reminder, we've got E equals h nu, and we've also got C equals lambda nu. So I'm going to write E equals h nu, got that equation, and we've got this equation, C equals lambda nu. So, in this problem, it says, what is the energy of a photon of radiation with a wavelength of that wavelength? And I'll give you a little warning there, that's given in nanometers, right? So obviously I have not given you the equation that combines energy, wavelength, and frequency. So we're not going to use just one equation for this. We're going to use these two equations. So how do I get energy? Well, it's energy right there, right? So I'm going to use the energy equals lambda nu. Well, I know h, I know that's the Planck's constant, I know that value, but I don't know the frequency to plug in yet. So in order to get that value, I'm going to have to use a different equation, C equals lambda nu. I know the value of C, and I'm given the value of the wavelength, but it's in nanometers, isn't it? So what am I going to have to do before I plug into this equation? That's right, I'm going to have to convert this many nanometers into meters. And then I'm going to have to plug it into here for the wavelength and solve for the frequency. And then I'm going to plug this frequency into this equation here and solve for the energy. So it's going to look like this. I'm going to do, in 3 steps, I'm going to do a length conversion of nanometers to meters. That will give me the wavelength in meters. Then I'm going to calculate the frequency. And then I'm going to calculate the energy. So this problem, it's a very easy problem to ask, but it's going to require 3 separate calculation steps. So now, having given you this overview of the 3 steps and the equations that we're going to use, I think you can do this. Pause the video and solve this problem, and when you're done, resume the video, and then I'll work through it for you. Okay, here we go. We know that we need to convert this wavelength from nanometers to meters. And once I get the wavelength, the lambda, in meters, I can plug it in here into this equation and solve for the frequency. And once I get the frequency, I can plug it in here and solve for the energy. So that's what I'm going to do. First thing is I'm going to convert my wavelength from nanometers to meters. So I've got 1.0, let's do my math down here. 1.0 times 10 to the 7th nanometers. And I'm going to do a conversion equals meters. So I know that 1 times 10 to the 9th nanometers for 1 meter. And if I do this math, I get 1.0 times 10 to the negative 2 meters. And that is my meters, the wavelength I'm now going to plug into this equation. So I set up that equation, C equals lambda nu, and I want to solve for frequency. So I rearrange the equation to solve for frequency. C over lambda equals the frequency. And I can start plugging in values. I know the value for the constant C, 2.998 times 10 to the 8th meters per second. I now know the value for the wavelength in meters, 1.0 times 10 to the minus 2 meters. And that's going to give me my frequency, and you can see that the meters cancel and I'm left with inverse seconds, or 1 over seconds. So I do this math and I get 2.998 times 10 to the 10th, and the units are 1 over seconds, and that's my frequency, right? Well, let me ask you a question. Should I round this to 2 sig figs at this point? I could, because the rule for sig figs is that multiplication and division says that I should round that to 2 sig figs, which would be 3.0 times 10 to the 10th. But here's why I'm not going to do that right now. I know that the next mathematical calculation I'm doing is also multiplication and division. So this next math step that I'm going to be doing uses the same sig fig rule as this does. And the general guideline for sig figs is that as long as you're continuing to use the same sig fig rule, then you wait until the end of that to do your sig fig rounding. That way you don't introduce rounding errors. So I'm going to leave that value as it is for right now. Now that I have my frequency right here, now I'm going to use this equation and solve for energy. So let's just do my math right here. E equals h nu. And I'm going to plug in h is the Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And my frequency I've calculated right here, 2.998 times 10 to the 10th inverse seconds. And we can see how the inverse seconds and the seconds are going to cancel and give me joules as my answer, as it should, because this is going to be an energy. So if I do that math, my calculator says that my answer, and now I'm going to round to how many sig figs? Well, back up here, I had only 2 sig figs, didn't I? So I can't retain all 4 sig figs in my answer, because all of this math, all of it was multiplication and division, so I haven't done any rounding yet, but I've got to go up to look at this number, and that came from my problem. There were only 2 sig figs in that problem. All of it was multiplication and division, so now I do have to round it to 2 sig figs. And so my calculator answer of 1.986 and so forth to the minus 23rd power has to be rounded to 2.0 times 10 to the negative 23rd units. It's energy, and we can see how we get joules out of that. And there's my answer. Does it make sense that this would be a very, very small amount of energy? Yes, because it's the energy of only a single photon. Absolutely. So that's how we can use these two equations, one after the other, to convert from a wavelength to energy. And of course, it would be a simple matter to reverse this whole process. If you were given an energy, you could use these two equations in turn to calculate a wavelength. So if you were given this energy, you would plug it into this equation and get the frequency. Plug the frequency into this equation and get the wavelength. And then if we'd asked for the wavelength in nanometers, then you would have to do a final conversion from meters to nanometers to get your wavelength in nanometers. Why do we see nanometers so much as a unit of measurement for wavelength? Well, it's a very common unit because it's easier for our minds to wrap around 400 nanometers or 700 nanometers than to talk about some number that has a large negative exponent. It's a lot easier to say 400 than 4 times 10 to the negative 7. Okay, one final comment I'll make, again, is that yes, we could indeed combine these two equations. If we were to solve this equation for frequency and then plug that value in here for frequency, you would get this right here. So I'm just going to do this as a side for your benefit to see where we can get the other equation from, because in your research and online and your reading, you may encounter this equation. And all it is just combining these two. So if I take this equation, C equals lambda nu, and I solve for nu, the frequency, I get C over lambda, right? Now if I take this value for frequency and I plug it in right there, you will get E equals H, and then for frequency, we're going to plug that in right there, C over lambda. And so this is an equation. It is a combined equation that combines both of those equations. And yes, you can use it, and you're certainly allowed to use this equation to convert from energy to wavelength just using one equation. But the reason I have emphasized the two equation approach again is because I really want to cement in your mind these two equations and the relationships between wavelength and frequency and between energy and frequency. Just one last reminder, at the end of this video, I will provide links to the two videos that describe a little bit more in detail about Planck's work with blackbody radiation and Einstein's work with the photoelectric effect, and how they are early examples of using the quantum theory to explain physical phenomena that the classical physics model was not able to explain.